Okay, all right, yeah. So let's start. So thank you very much for Dr. Pan's introduction. Yeah, it is my best time during my life now. This 5 years, my best time, I think. Yeah, so thank you very much for coming to my defense. And I would like to share all my works during my PhD study with you. And today my topic is location and data privacy preservation in intelligent systems. So here is the outline. I will first give some introduction about my PhD dissertation motivations, and then I will introduce two of my works. The first one is differentially private deep learning, and the second one is location privacy in mobile cross-sensing. And at the last, I will also introduce some of my other works. So let's start. So due to the ubiquitous mobile devices with embedded sensors and connectivity over the internet, the IoT is evolving, and the extensive set of applications for IoT devices is divided into four parts. The consumer application like smart home, and the organization applications like smart health systems, and the industry applications like smart factory, and also the infrastructure applications like smart grid. So the IoT brings explosive growth of devices controlled and connected by the internet. The data collection of these sensors and mobile devices has brought us to the big data era. So facing the big data era, the intelligent system has become an emerging paradigm for integrate the data analysis, privacy, and artificial intelligence. So the formal definition of intelligent system based on the U.S. Department of Defense is like this. So the intelligent system is any system that can do the manage data gathering, can obtain and process the data, and interpret the data, and also provide reasoned judgments to decision makers based on this data. So basically in the intelligent systems, we will first sense data from the mobile devices or sensors, and then this data will send to the intelligent system servers. And the server will help us do the decision making based on this data analysis. So in this case, as we are in the big data era, we are facing data explosion, right? So let's see what happened in an internet minute. We can see that in every minute, there are 200 million email sent, and around 2 million search queries on the Google, and also 3 hours of video has uploaded on YouTube in only 1 minute. So, and in the future, the growth of the data explosion is staggering. So facing this data explosion in the big data era, there are two challenges. So how to efficiently utilize such a huge amount of data, and how to protect sensitive and private data, as the data are all sensing based on the mobile devices or the sensors. So some of the data may be personal and also sensitive. So we need to protect this sensitive and private data. So let's see first about the first challenge, which is the data analysis. So because of the data explosion, there is a very important property of the big data, which is the veracity, which is also mean the data uncertainty. So we need to understand and quantify the data uncertainty, because data quality can vary greatly, of which can affect the data analysis accuracy. So let's see in a survey that around 27% of the respondents were not sure how much of their data was inaccurate or was inaccurate. And also 1 in 3 business leaders don't trust the information they use to make decisions. And also this poor data quality costs the US economy around $3 trillion a year. So we can see that the data uncertainty are everywhere. And also, let me give a very simple example to see what is data uncertainty. So for example, we are trying to test the temperature. So we will use a sensor, but in one property of a sensor is their sensor sensitivity, right? So the sensor will not give us an accurate measurement, but it will give us, like, for example, a range. And actually during the experiment, we are doing several rounds of this testing, and then we do an average. So in this case, the final temperature testing will be a range, so which bring us some data uncertainty. So the researchers have developed several methods to deal with the data uncertainty. For example, the data-driven method and fuzzy logic, and also the Bayesian analysis. So based on this technology, we can fully understand and quantify the data uncertainty. And another thing when we are doing the data analysis is we need to keep up with the continuous influx of data, right? Because we are facing a very huge amount of data. So machine learning has been involved during the last decade to deal with this huge amount of data. We can see that in 2009, the ImageNet has been generated by Professor Feifei Li, and in 2014, the generative adversarial network has been proposed. And also, Facebook has published their deep face, which can identify face with very high accuracy. And in 2016, AlphaGo becomes the first Go program which can beat a professional player. And also in last year, 2020, OpenAI has published a GPT-3, which is used to generate human-like text based on the deep learning models. So we can see that machine learning play a very critical role in the big data era, also in the intelligent systems. So based on these technologies, we can deal with the data uncertainty, and we can keep up with the continuous influx of the data. So another issue, another challenge in intelligent system is the privacy, as I introduced before. So we can see every day we are using the mobile devices, and there are many apps we are using. For example, social media app and some face recognition. So like we are using Face ID to unlock our cell phone every day, and also the speak recording apps, and also some smart house record app. And we also use GPS to navigate. So when we are using these applications, our personal data may be leaked. And here are two big events for the data breach. So in 2013, 3 billion users has been affected by Yahoo data breach. So the user's name, email address, or even their hashed password has been disclosed to some malicious parties. And also in 2019, 87 million of Facebook users has been affected by the data breach. Their data has been sent to Cambridge Analytica without any consent. However, in this data, there are many sensitive and private information. So in this case, our privacy information has been leaked. So there may come a question, what will happen if data leakage occurs? So the most important thing is the identity theft. So we can see from the left figure in 2019, 650,000 people are suffering from identity theft, based on the data from Federal Trade Commission, and it is a rapid increase compared to 2018. So from the cases of the credit card fraud to bank, tax, and loan, it is clear that the identity theft is more and more rampant. And another privacy issue is about the location privacy leakage. So if your vehicle has GPS systems, and your location and trajectory data is storing in a cloud. However, if this cloud is affected by any data breach, your historical location trajectory will be disclosed to some malicious party. So with this kind of data breaches, your life pattern and your home location may be leaked. So in this case, they can do some other crime on the victims. So it is very important for us to know how do we protect our sensitive information. So during my PhD study, I would like to generate privacy preserving and reliable data analysis in the intelligent systems. As I introduced before, we in the intelligent systems we have data aggregation, and and after the aggregation, we are doing the data analysis. However, during our data aggregation, we need to understand and quantify the data uncertainty, and also we need to consider about users' privacy. And for the data analysis, we can use machine learning or optimization to analyze the huge amount of data. And in my proposal last semester, I have introduced the integration work of privacy and machine learning for PP GAN, the privacy preserving GAN, and also I have introduced the location privacy in the mobile cross sensing. And today I will introduce a new work. It is also integrate privacy and machine learning, and it is the differentially private deep learning in the medical applications. And the second work, which is also introduced in my proposal, but now I would like to introduce it in detail. So it is integrate. In this work, I have integrated the privacy, data uncertainty, and optimization. So in these works, I'm trying to use differential privacy to protect the sensitive data. So before I introduce my work, I would like to give a brief introduction of differential privacy and how does it protect the data. So when we are trying to do the data aggregation, and after that, we would like to publish some information based on the database. We want so there is a question: what kind of information can be published? Because we want to obtain statistical information from a data set, but not the individual sensitive data. So for example, we can publish smoking causes cancer, but we cannot publish Mary smokes, so she may have a very high probability get cancer. So in this case, we will use differential privacy to protect this kind of data. Data privacy can guarantee that people can only learn the characteristic of the whole data, but individual data's privacy is preserved. So let me give an example here. So I will feel safe if I submit a survey. So whether or not I am in the survey, the query answer of this database should not change a lot. So in other words, the distance between these two query answers, S and S prime, should be at most epsilon, with the probability of 1 minus delta. So here epsilon is privacy budget and delta is probability of failure. So mathematically, it can be expressed in this equation. So again, if so I will feel safe whether or not I am in the database. The distance between these two queries should not change a lot. And now here I will give a formal definition of differential privacy. So the main point behind this definition is there is no much difference between the output of the a randomized algorithm over two data sets that only differ in one data element. And during in the differential privacy technology, we usually trying to inject noise to protect the data. So there is a question of how much noise should we add? And here are 4 properties we need to think about when we are trying to inject noise into the data. So the first two properties are privacy budget and the probability of failure. These two properties are shown here, the epsilon and delta. And another two properties is the sensitivity and also the type of noise to be added. So I will introduce these two properties now. So here is the formal definition of the sensitivity. So the sensitivity of a function is the largest possible difference that one row can have on the result of the function. So let me give a very simple example to show what is the sensitivity. So here we have two data sets that is only different in one row, and we have a query. First of all, we have the query of counting the total number of students. So the sensitivity should be 1 because there are only one row difference. So the largest possible difference is 1. And if we are trying to query the summation of total enrolled credits of all students, so it will be the sensitivity will be 12. So with the assumption that every student can only the maximum enrolled credits of student will be 12. So in this case, the largest possible difference between these two data set will be 12. So that is the definition of sensitivity. And now I will introduce what type of noises should be added. There are two kind of distributions are usually used in differential privacy. The first one is Laplace distribution, and the second one is the Gaussian distribution. And we can see from these equations, the larger sensitivity, which is represented by this big delta. So if we have a larger delta, the variance of the Laplace distribution will be larger. So in this case, we will have more distortion. And let's see from the right figure. So if we have a smaller epsilon, our variance for the Gaussian noise will be larger. So in this case, it will provide a better privacy because the noise added to the data will be maybe larger. And again, the delta means the probability of failure. And actually, in differential privacy, there are many flavors of differential privacy definitions. So the difference between these definitions is how they quantify, how they quantitate the privacy loss. So here we are defining the privacy loss with this equation, and it is the differences between these two probabilities. So in the epsilon differential privacy, it is very strict, and it is the probability of this privacy loss should be smaller or equal to 0. And for the other two, different privacy definitions, they have some relax. So actually, in my during this presentation, I have used epsilon differential privacy in my second work and used these two definitions in my first work. And because there is very important properties for the rho omega truncated concentrated differential privacy, which is it can provide simple, explicit, and tight privacy bound analysis. So in this case, I have used these definitions in my deep learning applications because there are many iterations during the deep learning. So and the privacy budget will accumulate it. So in this case, we are trying to use this rho omega TCDP, this definition, to provide a very tight privacy bound. So that is all for the introduction about different privacy. And now I will introduce my first work, differentially private deep learning. As we know that deep learning holds a great promise of revolutioning the healthcare and medicine. And there are many applications of deep learning in medical. We can use deep learning for medical imaging analysis, and we can identify disease and do diagnosis based on deep learning. And we can also use deep learning to do personalized medicine. However, However, deep learning is suffer from many inference attacks. For example, the membership inference attack. So in this inference attack, a malicious party may know that whether a person is in the training dataset or not, only with the access to the final trained deep learning model. So if this training dataset is a sensitive dataset, for example, the criminal history dataset or some specific disease dataset. So if the malicious party know that one person is in this dataset, so he may know some sensitive information about this person, so which we do not want to see, right? So in this case, this is the membership inference tag. And another inference tag is the model inversion tag. In the model inversion tag, we can reconstruct the image data. We can reconstruct the training image data based on the output of the deep learning. So we do not want to, so in this work, I want to protect the training data against this inference attack. So here is what I do in this work. So here is a general process of deep learning. We have some data, we have some private data set, and it is input, and we will do the training, and then we will output the training model. So here is a privacy barrier. So some malicious party can only access to this output. So we can assume that malicious party are the health insurance company, because they are very curious about their users' history, disease. So in this case, they can give different plans to different users to gain more profit, right? So if this, as I introduced before, there are many inference attacks against the deep learning. So in this case, if this malicious party has the access to the trained model, so it will get the information from the private dataset. And in my work, because I'm trying to protect this private dataset, I will train this dataset with differentially private solver. In this case, we will get a private trained model. So although the malicious party has the access to the output, our private dataset should not be leaked. So basically, I'm trying to inject differentially private noises into the gradient during the training, and that is how we do this private training. So now I will introduce the detailed process to do this DP training. We have this, again, we have this private dataset, and we have some neural networks. So the first procedure is we want to compute the gradient. And here L is the loss function. And we may use the SGD to do this gradient descent, and we will update model parameters. And because we are trying to inject the DP to the gradient, so as we introduced before, we need to quantify how much noise should be injected into the gradient. And there are 4 properties, right? The privacy budget, epsilon, the probability of failure, delta, and the sensitivity, and also the type of the noises. Here, in order to quantify the sensitivity, we need to do the gradient clipping. So with this clipping bound C, we will bound the gradient into the C. So clip the gradient. In this case, we can quantify the sensitivity and decide the amount of differentially private noise which is injected into the gradient. And then we need to choose what kind of noise should be injected into the gradient, right? So here we are trying to inject linearly decaying Gaussian noises. So here R is the decaying rate, which is a number, which is a value smaller than 1 and larger than 0. So because we can imagine that if we are injecting constant Gaussian noise into the gradient, the training may be break it. The the model will not converge. So we are in order to improve the utility of the deep learning model, we will trying to add linearly decaying Gaussian noise. In this case, the noise will the injected noise will be smaller and smaller during each iteration. In this case, we can improve the utility of our private deep learning model. And here is the overall algorithm of this work. So at the beginning, we will initialize this we will initialize the variance for the Gaussian noise, and then during each iteration, we will compute the gradient clipping with the clipping bound C. So we will first do the clipping, and then we will add adaptive Gaussian noise, which is linearly decaying Gaussian noise. So with the variance sigma here, sigma there is a linear decaying rate R. So every time we will inject smaller and smaller Gaussian noise into the gradient during the iterations. So in this case, during each iteration, the privacy budget is represented in this equation, and the privacy budget will accumulate during each iteration because of the property of differential privacy. And so in this case, the overall privacy budget for this training is showing these two equations. So we have this R is the linearly decaying rate, and we have the sigma, which is the initial noise, the initial noise variance, and also we have C as the clipping bound. So as I introduced in the DP definition before, that the rho omega TCDP can also translate into the epsilon delta DP. So in this case, we can compare our proposed method with the existing method in the literature. And now I will show the experiment result. So in this experiment, we are using a real world data set called CheckSpert. And in this data set, there is the chess X-ray images. And we are using the DensNet 121 to train this model. So here are the training accuracy. So we can see that this blue line, these blue curves are the existing method, which is called DPSGD, which is just inject constant noises into the deep learning model. But here we are trying to add, for the red curve, we are trying to inject linearly decaying Gaussian noise into the gradient. So in this case, we can see that our performance is better than the existing work, and also because there are 5 classes, so I will showing 2 accuracy here. And again, the epsilon is the privacy budget, so a smaller epsilon value means a higher privacy level. So we can see that if we set the epsilon is very smaller to 0.5, the performance cannot be good enough. However, if we set it to a larger value, like 2 or 8, our performance is much more better and much more close to the optimal non-private deep learning model. And also in this work, there are several important properties like the decaying rate and the clipping bound, and also the initial noise scale. So here I'm showing how should we choose these values. So here we are trying to find out what is the best value for the decay rate. So here we can see that with a higher decay rate, the training epoch number will be higher, and the 0.99 should be the best selection for the decay rate, which can provide the best solution. And for the clipping bound, around 1 is the best solution for the clipping bond. And also for the initial noise scale, we can see that maybe around 2, the initial noise scale around 2 will be the best solution for our work. So these are the parameter analysis for our algorithm. And we also tested our training model we also tested our schemes on these two data sets, the popular data sets, the MNIST and the Sapphire-10. So here we can see that our proposed method outperforms the DPSGD. So in the MNIST dataset, our test accuracy is 1% and 0.2% and 0.2% higher than DPSGD. And for the Sapphire-10, our proposed method, the accuracy is promoted by around 6% and 3%. So in this case, we can see that our proposed method can protect users' data at the same time improve the data utility. And that's all for the first work, and here are some takeaways. So in this work, we have proposed an adaptive differentially private deep learning algorithm by injecting linearly decaying Gaussian noise into the gradient during each iteration. And we used the truncated concentrated differential privacy, the rho omega TCDP, to quantify the data, to quantify the privacy bound. And also we have used the real-world chest radiograph dataset to validate our effectiveness of the proposed method. And that's all for my first work. And now I will introduce my second work, the location privacy preservation in mobile cross-sensing. So here is a question: what is mobile cross-sensing? Actually, mobile cross-sensing is what we are using every day. So in the mobile cross-sensing, there are 3 parties: the task requesters, maybe some grocery stores or restaurant. And here are some MCS servers, for example, the Instacart and Uber and other things. And here is the third party. Which is drivers. So the drivers will finish these tasks based on their request. So the task requester will send task requests to the MCS servers, and the MCS servers will assign tasks to each worker, like here the driver, and the worker are subject to send their locations back to the server and move to the task locations to perform the task. So that is the overall system of the mobile cross-sensing. However, when the workers are doing their tasks, their location may be leaked. So because the workers are supposed to periodically send their locations to the server, so the server can do the task allocation based on their locations, right? However, many location data breaches has happened in the last decade. We can see that, for example, the IQ weather, it is an app for the weather. They are affected in a data breach because when the user are using this app, their location data will send to another company, whether or not the user is allowing the data share or not. So in this case, if our location is shared by a third party, so the third party may be malicious party. So in this case, our data privacy is disclosed. So with our location data, the malicious party may know our home locations, our work locations, and also know our life patterns. When will you go to work and when will you go to the gym? So in this case, the malicious party may do some physical crimes based on these victims. So in this case, in this work, we are trying to protect the worker's location privacy. So basically, we are trying to use the local different privacy, which means the privacy algorithm is performed locally. So only the worker will know their true data, and then they will send an obfuscated location data to the server. And here is a formal definition of local differential privacy. Actually, it is just similar to the centralized one, but here the input are not the data set, but 2 data points. So in this case, if we have 2 different input x and s prime, the malicious party cannot distinguish whether which is my true location. So, and in order to satisfy this local differential privacy definition, we are trying to use the Warner model, which is published in 1965. So in the Warner model, it is basically used for survey. So if there is a private question, do you have any history of mental illness? So you may not want to tell me whether or not you have this illness. So each person will flip a coin, and if it is a head, you just answer choose, or if it is the back, you just answer randomly. So in this case, each person with mental illness will answer yes with probability of 97%, and answer no with a probability of 25%. And this kind of model is unbiased estimation of the distribution, because if there are NV out of N people have mental illness, we can expect the yes answer with this expectation, right? And then we just define this CNV as the unbiased estimation based on this equation. So the expectation of this estimation is equal to NV. So in this case, we can see that the model is unbiased, is doing the unbiased estimation. So in this case, the data privacy will be protected. However, we are still know the characteristic of the data distribution. So that is what we are trying to do in this work. So in order to apply the LDP, the local different privacy, into the mobile cross-sensing, there are 3 steps. The first step is encode. So for example, we have a location, input location L. So in the first step, it is executed by each worker. So the worker will first encode their data and output the value C. And with this encoded C, the worker will do the perturbation. So we can take an encoded value C and output a C prime. So each worker will only report this C prime, which is obfuscated code, to the server. And then the server is doing the task allocation based on this obfuscated locations. So the task allocation is executed by the MCI server, and it takes all the reported obfuscated code and assign tasks to workers based on the travel distance. So we can see that these 2 parts, these 2 procedures are done by users, and this part, task allocation, is done by the server. So let me introduce these steps in my work one by one. So the first part is encoding. We are trying to use this geocoding systems. So we can see that the geocoding system is something shown here. This is an example. So a geocode can represent a geographic entity, which is a location or an object. So after this encoding only 1 index instead of the traditional 2 joint index, the latitude and longitude will be sent back to the server. And the query for this 1 index are much faster and more efficient than these for 2 joint indexes. So in this case, we are using the geocoding systems to encode the worker's location. And then we are doing the perturbation based on this geocode. And we have proposed two methods. The first called grid DPG. So for example, if you have a true code 1, you have the probability of P to keep this code, and another probability of 1 minus P to flip it to 0. So in other words, the probability of bit flipping is this amount of probabilities for G bit suffix. And another perturbation method is called geohash DPG. So here, for example, we have the true code 0000. So we will keep it as the original with the probability of P and perturb it to all the other different code with a probability of Q. So here we have we assume that in total we have H geocodes. So the P should equal to this amount and Q should be equal to this amount. So in this case, the P plus H minus 1 times Q is equal to 1. So these are two perturbation methods we have proposed in this work. And next is the task allocation by the MCS server. So the server will formulate this travel distance minimization problem. It is very simple here. We can see that this xij is an integer parameter, so it indicates that whether a worker is assigned to a task. And there is a constraint based on this integer parameter. So this inequality means each worker cannot be assigned more than one task. Okay, and also another constraint based on this integer parameter is each task must be finished by a worker. Okay, and also this D here is the distance between a worker to a task. So, and because we have do the perturbation of each worker's location, so the distance between each worker's obfuscated location and the task location is uncertain because of the LDP algorithm. So here, in order to solve this optimization problem, we need to deal with this uncertainty. But fortunately, as our obfuscated scheme has just perturbed the true geocode to the other geocodes, so we know all the probabilities in this randomized mechanism. So in this case, we can leverage the conditional value at risk CVAR to try to solve this optimization problem. So the CVAR is something like this. So we can see that the x-axis is called the loss, and we have alpha called value at risk. It is VAR. So there is a probability of 1 minus beta that the loss is larger than this alpha value. And the CVAR is the conditional value at risk, which is the expectation loss in this distribution with the probability of 1 minus beta. And here, beta is the confidence level, which can be chosen to as the 90%, 95%, or 99%. So in order to use this CVAR, we need to first define our total travel distance as this f function, so which is our optimization problem. So now we are trying to minimize this f, and then we are transfer this function f to a CVAR expression. So here the CVAR is shown like this, and we need to calculate the expectation of this function with this alpha. So in order to approximate this expectation, we are trying to use Q samples from this distribution. In this case, we can approximate this expectation. So that is how do we solve this optimization problem. So here is our original optimization problem, and then we transfer it into a CVAR minimization problem. So we need to minimize both the x, the integer parameter, and the alpha. So now this proposed optimization problem is an integer linear programming problem, which can be easily solved by branch and bound algorithm. So so that is what I have done in this work, and here is some simulation result. So we have also used a real world data set, which is the taxi location dataset of Rome. And here is the distributions of these taxi locations. We can see that most of the location data is distributed in the downtown area. So we just choose the downtown area for our simulations. And here is the true location distribution. We can see that in these two parts, there are many taxis. And here is the perturbed location distribution. We can see that overall, because some of the location has been perturbed, so the distribution has been changed a little, but the distance between these two should not change a lot. And we are in this simulation, we are using the evaluate matrix mean travel distance, which is the average travel distance of the selected worker to the selected task. So here is the two important parameters in this CVAR, which is the beta, and the number of samples which is selected for approximate the expectation. So here the beta is the confidence level. So we can set it to 0.9 or 0.95 or 0.99. So we can see that with a higher beta value, the total the mean travel distance is larger, and if we are trying to select more samples, the mean travel distance is more closer to the no privacy value. And also we have compared our proposed method with this geo-indistinguishability. The geo-indistinguishability is the existing method, which is just inject Laplace noise into the longitude and latitude to the worker's location. So we can see from this simulation result, our schemes outperforms the existing geo-indistinguishability algorithm. So that is all for my second work. And here are some takeaways. So in this work, we studied the optimal MCS task allocation problem by minimizing workers' travel distance. So in order to protect the workers' location privacy, we have used the local differential privacy. And also, in order to solve this optimization problem, we leverage the CVAR to deal with the uncertainty, which is brought by the local differential privacy. And in the simulation, we have used the real-world taxi location dataset to validate our effectiveness of the proposed approach. So that is all for my second work. And now I would like to introduce some other works during my PhD study. So the first one is the risk detection with deep learning for offshore drilling. So this is a project collaborated with Shell. So we have the drilling videos as the input, and we use the CNN and optical flow to detect the movement of this video. And in this case, because several risks may happen during the offshore drilling, for example, the well has sucked in or some burst. So in this case, we are trying to detect if there is any risk happen based on this video. So here is our result. So sometimes it is sandy and sometimes there is a gumbo burst. And here is a risk we have detected the well has sucked in. So here the drilling fluid is turned to 0. In this case, we have detected the risk. And another work is a COVID-19 symptom map construction. Because we are in the pandemic, so we want to utilize our knowledge to help the community to like defend ourselves. So in this case, we want to know what is the next outbreak communities without violating people's privacy. For in this case, we can dynamically allocate the limited healthcare resources. So in this case, we have used the federated learning to collect the data and train the model for them to predict what is the next outbreak community, and then we can do the allocation dynamically based on this kind of vulnerability map. And I have also done other works, the privacy preserving cache in information-centric networks. So we have content provider and the users. So the users want to protect their privacy and download their favorite content. And the content provider want to maximize their revenue and to estimate what is the popular content from the existing sampling users with data-driven approach. And also I have done the privacy preserving participant recruitment for coverage maximization in mobile cross-sensing. So these are the works I have done during my PhD study. And here is my publications. And that's all for my presentations. Thank you. So is there any questions?